Thank you so much. I'm sorry, guys, it's 12 p.m. and you will hear a carillon because I'm living by a church. So for 10 minutes, you will hear a nice carillon behind me. But so that's, it is what it is. Thank you, Paul, for your presentation. I really, really hope I will not contradict what you've been saying all the time with my presentation, and I hope I will really make honor to what you've been saying. So let's see if, okay, someone can tell me that you see.
Yes, we do.
Yes, okay, and I will use a pointer if I can. Yep, that will be okay. So today I just wanted, and sorry, I will just close my switch off my camera because it will be easier in terms of streaming. So today I wanted to discuss about the lipophilicity by chromatography, because by background I am a separation scientist, and I'm a big component of separation science that can be used more than to separate compounds, also to study interactions. And from lipophilicity, what other descriptors can we study, or at least kind of touch to optimize Phys-Chem properties. So quickly, I will show you, of course, and kind of a reminder, the role of lipophilicity in drug design and how we can measure lipophilicity using HPLC, and what are these other additional Phys-Chem descriptors such as conformation and intramolecular gene bond. And then we can summarize the key concepts here. So for me, the lipophilicity is a driver in drug designs, because so it will really lead the permeability that will affect, or that will influence, I would say, in vitro and in vivo ADME properties, impacting the oral bioavailability that will be used to determine, that will be helpful to determine the clinical dose. So if we go to permeability, what is permeability? Permeability is really the velocity of a molecule to cross membrane barriers, knowing that for gut membranes, you have, it's a bilayer membranes, or in fact 3 layers if we consider that we have the polar heads, the lipidic chains, and again, another polar heads in contact with the plasma, so the blood. So you have different types of permeability, and the main one is more the passive permeability, where it's really through sample diffusion based on the difference of dielectric constant between what is outside a membrane and what is inside the membrane. You can also some have ion channel, but all this permeability we usually measured by PEM permeability will really evaluate, is based on the lipophilicity. And you can imagine that some drug that is more hydrophilic than lipophilic will have more solvation in an aqueous solvent, and will have less interactions with a lipidic layer of the membranes. When a compound has some hydrophobicity, you will reduce the number of interactions with the water, and you will have more interactions, or hydrophobic interactions, with the lipidic phase of the membranes. And when it's too hydrophobic, that's the caveat where the compound might, if it goes through the polar heads, will stay in the lipidic phase. So it's always a question of balance between lipophilicity and, of course, between size. So because a large molecules maybe will have less probability to cross the membranes, because you still have to kind of, I would say, change the shape somewhere of the compounds and of the membranes, and also based on flexibility, that could be the carbon sp3 mentioned by Paul. Then also how then it will influence, I would say, the in vitro and in vivo ADME property. It's more, so if we stay with in vitro ADME properties, you understand that the compounds will have interactions with the different tissues being either way, so the protein in plasma, but also the proteins and the lipids in the tissue compartment. That will influence the bound fractions or the unbound fractions, and the distribution of the compounds. In terms of absorptions, The intestinal absorption is determined as a product of solubility and permeability. So you can really quickly understand how the lipophilicity will also impact the absorption. Then we have this effect on the metabolism and clearance. We know that a compound that has in the first pass metabolism, a compound that has a high lipophilicity will metabolize, will oxidize a lot. And here, Obak had done this study on for IV administration. When you have a high lipophilic compounds, above 4, we have a high clearance compared to the renal clearance, where it's more the polar compound that will be cleared quickly. And when you have a lower lipophilicity, you will have a higher clearance in terms of renal clearance. So really, we can see how the lipophilicity impacts the different ADME properties. Now, in terms of toxicity, so the concept of having a compound that is very greasy will stick everywhere, will have non-specific binding to some extent, and will have affinity for a lot of different protein and tissues, and there will be a loss of selectivity and just even touching the target, and that's what we call kind of promiscuity. And David Price had shown that for a compound with a cLogP above 3 and a low TPSA, we would have a higher toxicity. One of these in vitro toxicity is a HERG, or the cardiac potassium channel, and where you need to be in the safe zone to avoid this fatal cardiac arrhythmia, you need to have an inhibition for compounds about 10 micromole. And Waring had shown that, so in their sample bank, neutral comp, so 75% of the neutral compound had an inhibition above 10 micromoles, or were HERG safe for a cLogP below 3. In terms of bases, it was a little bit lower because they had 50% of their bases were HERG safe for a cLogP below 3. So again, the impact of lipophilicity on these toxicity properties. So then, in terms of oral bioavailability, this oral bioavailability is a product of absorptions and metabolism. And we've just seen that lipophilicity impact absorption through permeability, and lipophilicity impact metabolism and clearance. So again, lipophilicity will impact somewhere this bioavailability. So all over the development of a compounds toward a good oral bioavailability, the lipophilicity is one of the main driver. So Marina Shalaeva, when she was in my group at Pfizer, had put this nice summary where would be the ideal range of lipophilicity, and really you stand when you have a lipophilicity cLogP or logP between 1 and 3, because you get a good balance between solubility and permeability, and with an optimal intestinal absorption and a reduced metabolism. Compared to when you increase the lipophilicity, you will still get a good permeability, but you will have more metabolism and you can go through higher toxicity. And for a compound that has a low lipophilicity, you get a good solubility, but really your passive permeability is badly impacted, and you have a high renal clearance, because that means somewhere that your compound is lipophilic. So as a way to illustrate that, I tried to find there are plenty of illustration on the paper, but I really wanted to compare compounds that are equivalent, and that was this idea of finding diastereo-isomers for here these zwitter ions, where you have a pK of the acid that is above around 3, and for the amine this is around 8. And so these two compounds have already by shake flask different lipophilicity. And what happens is, so you would expect that the more lipophilic will have a higher metabolism based on what we said, which is the case in terms of oxidation, but compared to the second one. But at the same time, so the first compound had a good AUC and a decent oral bioavailability compared to the second one. So which makes sense. What doesn't make sense here in this study is somewhere that the KCO2 permeability, so this is a permeability based on cell with transporters, is kind of similar, and you have the efflux, however, that is not similar. So The authors, they say that it was, in that case, the transporter were not playing a role in all the drug design and in the transport of the compounds. But question is, what if they had measured the PEMPA? Probably the PEMPA permeability would have provided a completely different permeability just based on the lipophilicity. That's just my comment. So now let's go to, so just a reminder, what is lipophilicity? Maybe that I should have started with that, but this is really this tendency of a compound to dissolve in a lipid or oil, and we really calculate this as the log of a ratio of the compound dissolved in this lipid oil over water. And we have two types of lipophilicity when we are working with non-ionized solute or when we are working with ionized solute. So the log P is a ratio of non-ionized solute, and the log D is a ratio of the compound that is both either way ionized or non-ionized. So having more compounds soluble in water when it's ionized, usually we have a log D that is lower than a log P. But log P helps in terms of exposure, understanding exactly what could happen in the tissue. So now, how do we measure lipophilicity? So basically, the standard method is using the shake flask. So shake flask was a way to mimic the membrane. So you use the octanol, that is a kind of a long CHN with some polar group that could mimic, in fact, the lipidic layer of the membrane and the phosphate or the polar head. So the dielectric constant is a little bit different, from the membrane, but still that was the best model that was used to get experimental data from lipophilicity. So usually what you do, your compound is from DMSO, you dissolve it. So in water, you add the octanol, you shake, and you wait for the compounds to partition between the two phases. And what you do is you measure, either way by UV, by LCMS, LCMS-MS, the quantity of compound in each phase. So the caveat to this method is when you are going through highly lipophilic compounds, they all reside in the upper phase, and you have very few compounds in the water, and you may be at the limit of quantification. So when you have then a ratio, because this is a log, a ratio, difference ratio between an octanol and water phase, when this ratio is about 10, the log P will be added by 1. But when this ratio is of 1,000, in a log P, it's translated by 3. So the margin of error, when you have a compound in the extreme, either way, highly lipophilic or in the same way, highly hydrophilic, and where here you will decrease your log P by 3, creates kind of uncertainty. And usually the quantification really depends on the compound solubility in each phase. And when we were working at Pfizer, working with HPLC UV only, we had found that the shake flask was a quantitative technique, and we could get a 95% confidence for lipophilicity between 0.5 and 2.8. I have to say that now with more sophisticated method, quantitative method, by LC-MS-MS, you can decrease this limit of quantification in each phase, and you have a better reliability for higher log P or log D around 3 and 3.2, but you are still limited in terms of higher lipophilicity, and it's getting more difficult to characterize compounds that have so large molecules such as PROTACs. I will not use the beyond rule of 5 molecule. So now another way to measure lipophilicity is to use reverse phase HPLC, because reverse phase HPLC is a C18 support that could mimic, the lipidic phase, and you use some water in the mobile phase because this is reverse phase, and that could mimic also this idea of hydrophilic heads. You have a C18 directly, or you could have also a C16 amide support, the amide groups really playing the role of the polar head. There are also platters of other stationary phase. You have this IAM support. This is the high mobility affinity membranes. And this is really with the sphingolipid and phosphate. to mimic the polar heads that is close to the phosphate heads of the membranes. I will not develop this more because Giacomo tomorrow will discuss about this IM and all the information we can get from this analysis. And there is another support I would like to mention, and this is what we call the PLRPS, the polystyrene divinyl benzene. That is completely hydrophobic. There is absolutely no silica. This is a polymeric support. And you can imagine that heat plays the role of really it mimics the lipidic phase of the membrane and how we can use this in terms of understanding lipophilicity and further permeability. So now I will describe more carefully the C18 and the C-AMID supports and why chromatography. So chromatography, it will be not a partition, but it will be a distribution between two phases and what between the stationary and mobile phases. And what we study is hydrophobic interactions. And the more hydrophobic the compound is, the more interactions there will be, so the more retained the compound will be. So you will have a higher retention. This is, of course, a qualitative measurement. This is not a quantitative. So that means we are less limited by the solubility of the sample in the HPLC systems. And because we measure retention time, you can increase the length of your columns as much as you want. You can modify your mobile phase, but we can really and reproducibly measure high lipophilicity up to 7, 8. You can use different buffers as you would do on a shake flask, but you have also the diversity of supports as I've just described before, and you can study a lot of these supports can mimic a lot of different membranes and we can have different types of interactions, but mainly hydrophobic. I just read a review where they were listing about 80 different conditions between stationary phases and mobile phase just to study lipophilicity. So what we will do in terms of chromatography, we will always study the K prime or the K, that is a capacity, sorry, it's a log, it should be a log. That is a capacity factor, that is the sign as what we have a good retention on the compounds because it elutes after the dead volumes, meaning that we have optimal interactions between the compound and the support. So I will start with the chrome-LogD. So chrome-LogD has been developed by at GSK by Clara Valco's group, and Clara has written so a great chapter on her book about the chrome-LogD. So the idea is really to have in a high throughput to define an hydrophobicity index, chromatographic hydrophobicity index based on C18 at different pH. So what Clara has done is she has taken a lot of different standards and she has allocated a chromatographic hydrophobicity index by calculating the amount of acetonitrile that would be needed to elute the compound at a retention time that is twice the T0, just to make sure that all the compounds were properly eluted and had that all the interactions were really shown on this support. Then, so she has allocated this at different pH, so this CHI at different pH, and this creates a standard where you can create a calibration curve with that has a good R square, and where the retention time is, or the CHI is dependent on the retention time as the size of hydrophobic interactions. So once you have this calibration curve on your C18 support, then and you work with a gradient, then you can inject a studied sample and you get the CHI. The CHI is converted to the chrome-LogD at a certain pH with this equation that has been developed at GSK. So how do you use this chrome-LogD? So either way you can use the chrome-LogD with at just one pH and you will create your model, and I'm sure Rob tomorrow will show you how this fits well with a lot of different models. But also this is interesting because you can work at 3 pH, you could work at plenty of different pH, and what you will get is when your compound is ionized, you have different chrome-LogD. When your compound is not ionized anymore, then you get the chrome-LogP, and from this chrome-LogP, you can you can have an idea of the exposure. You can also get this PFI, so the property index that Paul just mentioned, and that I'm sure Rob will mention tomorrow, and you can get an idea of the intrinsic solubility. Another way also is if you work with a compound you don't know, when you see an increase of the log-D from pH over the 3 pH, that means you started with an ionized compound that was highly soluble in water, less retained, less hydrophobic interactions on the support, and then you increase the log-D with increasing the pH. So you go to a more insoluble compound in water, but more lipophilic compounds. So that means you have a base. When it's constant, that means you are in a neutral species. And on the other hand, when you decrease the log-D over the pH, that means you have an ionized form by the increasing the pH, and you are in presence of an acid. So it's kind of different ways of using different type of information you can get from one system. Now I will switch to the system developed at Pfizer by Franco and Lombardo and Marina Shelaeva. And so the idea was really to mimic the shake flask, but to be able to work in a higher throughput and to really highlight the interactions, so the hydrophobic interactions. So to do that, Franco and Marina, it shows the RP amide support. So it's a C16 amide support where you have this NH CO, and the carbonyl of the amide group on the support is an H acceptor, and so you have additional interaction with the H donor of a compound, and that is more emphasized when you have low lipophilicity. How does it work? So here, instead of working with a gradient, you work with an isocratic mode, and you work with a range of isocratic methods, for example, very narrow amount of methanol, 40, 45, and 50, and you calculate the log K prime, and from there you deduct, the log K prime W, meaning at 0% of methanol, and they have shown that this log K prime W could correlate with most of the log-D octanol shake flask method in the literature using this equation. So, however, how do you work when you work on an unknown compound? You need to have a predicted value to tell you if you work on a middle range, that means between 40 and 50% of methanol, or if your compound is supposed to be less lipophilic, you will work with a range between 20 and 30% of methanol, or if your compound is supposed to be of high lipophilicity, you will work with a higher content of methanol. So this is more a kind of lower throughput because you can have 9 methods. The idea is also that you need to have pre-calculated or predicted lipophilicity. So if the predicted is not good and you think that your compound is of middle or medium lipophilicity and suddenly nothing is retained or it's too retained, you have to go back to another range of method, and it's a little bit cumbersome. In addition, at the time where the assay was developed, it was more basic and neutral compounds that were developed in drug design. So the idea was to use ion pairing and to be able to study the basic compound at pH 7.4, where they are mostly positively ionized. We would use a counter ion that would be the morpholino sulfuric acid, the MOPS, and then also because the support, the stationary phase in 2000 were not as optimal as they are right now. You still had a lot of residual silanol that you had to mask using the decilamine. And you still need to have a little bit of octanol, kind of 0.5% saturated in water. This is a very difficult mobile phase, and the decilamine creates a lot of issues. And we have seen that over time, the support, the RP amide support was decreasing, the quality of the support was decreasing, and the vendor couldn't get a very more reliable support. So what Annalisa has been doing, they have modified, or I would say they have kept the same principle and mindset in terms of eLogD, but they have been using a new phase that is still an RP amide, but working on semi-porous particles just to enhance the exchange between the solute and the stationary phase. Because of the quality of the stationary phase, you don't need to use the decylamine. And because of all the exchanges, it has been decided not to work in ion pairing. So suddenly the system is made easier, but the idea was to still keep isocratic method, because interactions are kind of always similar from on the isocratic mode. So, however, to avoid the issue of working with predicted values, the idea was, oh, can we use a kind of scout method? So either way, starting at an isocratic method with 45% of methanol, or working with a gradient to evaluate where the compound will dilute. So either way, on an isocratic method, it was found that if the compound elutes at less than 5 minutes or less than 11 minutes on a gradient, you could work with a lower amount of methanol, compared to when the compound elutes with a higher retention time, 5 minutes, above 5 minutes on isocratic, or above 11 minutes on a gradient. This means that the compounds will be highly lipophilic and will require a higher amount of methanol. So at the end of the day, you reduce the number of methods, but you also reduce the number of uncertainty, because really you don't predict anymore, you don't use any model, but you really base your decision on what's happening on the columns based on the hydrophobic interactions. So all of this has been published in Journal of Chromatography in June, beginning, mid-year. So now, what's happening in terms of, if we want to understand what's happening in terms of chromatography. So Julia Caron has developed a model, PLS model, called block relevant analysis, where she has blocked, so defined different type of interactions and giving a weight to these different interactions based on the chromatography. So she has different blocks. One is the volume and the surface. The other one is molecular polarity. The other one is the hydrophobicity, H-bond donor, H-bond acceptors, and any others. And she has given colors. When she studied the eLogD, she found that there was a huge, so the eLogD, and in terms of these interactions between compound and stationary phase, were basically based on size. So size meaning molecular weight, volume, conformation. You have, of course, a negative component of polarity. Weirdly enough, the hydrophobicity is kind of zero between the positive and negative component. You have a little bit of H donor properties and less of the H acceptor. So as a way to illustrate this, I've tried to find some literature which is a little bit difficult, but here it's Matt Perry just mentioned on LinkedIn that they had found a kind of weird findings when they were looking for lipophilicity, were measuring lipophilicity of these compounds. So these compounds lipophilicity has been evaluated by shake flask, and these compounds are of high lipophilicity. That being said, when they were calculating the lipophilicity of this compound, or predicting using ACD or their own eLogD, when you increase this X substituent from 5-member rings to a 6-member rings, you could expect having an increase in lipophilicity. That being said, what they observed was that they saw lower lipophilicity. And when they went further, they explained this by, the conformation of the molecule, the compound with the 5-member rings being more had some planarity compared to the one with 6-member rings that has a more orthogonality. So if one is more planar, you can envision that it will have more interactions with any lipophilic system, and this could explain why the LogD, the higher LogD. I'm sure that if they had done this with eLogD or any chromatographic method, they would have had maybe more accurate or values of logD, but they would have been in the same trend. Now, if we continue with this volume and conformation, of course, we can always think about, intramolecular gene bond. So Scott Lockey had shown a long time ago that a compound, when the compound before going through a membrane, compound will have solvation and will create inter-hydrogen bond with the aqueous solvents. But how can we explain that this compound that has a certain volume and conformation can go through a lipidic phase and again cross this lipidic phase to go back to the bloodstream? The explanation was at one point there will be an energy barrier to cross for desolvation and to have a new conformation, and the compounds will have, in fact, instead of having inter-hydrogen bond with the aqueous media, will create intra molecular hydrogen bond, and to expose, in fact, the lipophilic functions of the molecule with the lipidic phase of the membrane. So the question, and because we still had a good passive permeability, so the question would be how could we measure, a lipophilicity in a lipidic environment, knowing that if the shake flask is limited by the solubility of the compounds, when you have octanol that has still some polar groups and water, how do you do with an alkane? So I've not prepared this slide, but I know, so Matt Naylor, and he's in the audience, Matt had done with Scott Lockey, they had developed this LogP decadiene, so shake flask with a decadiene where they would measure the lipophilicity of all their cyclic peptides and directly correlate this to the permeability. If we want to stay with HPLC, what we had done as work, we had found that, remember the PLRPS, the polystyrene divinyl benzene columns, we found that by this creating the system where we would have 80% of acetonitrile that is completely aprotic, with a little bit, however, of water, we would have working on different standards with calculated, which has calculated log-P in toluene, we could have a good correlation between this, what we call log K prime 80. So this is really having the capacity factor of these compounds with 80% of acetonitrile, and we would have a good correlation with the calculated log-P in toluene. Going again with the same idea of understanding the intermolecular forces that drive the retention on these columns, we found out that again you have the volume, so the size, so meaning the volume and the conformation of the molecule, that is a big component of the retention of the interactions of the compound with the stationary phase. Of course, you have less polarity, so you have a negative component of the polarity, a little bit better in terms of hydrophobicity, but what also is interesting is you have a very negative component of the H donor, because more compound being more polar will be less retained on this system that is completely lipophilic. So how does it translate on compounds? So what we've done, we're trying to make the proof of concept. We worked with match pairs, and we tried to find controls without intramolecular gene bond and samples with intramolecular gene bond. This the presence of this intramolecular gene bond was proven and confirmed by NMR and by the temperature coefficient. And here you have an example of these two compounds where they have exactly the same formula, but one without intramolecular gene bond has a low log K prime, so meaning low retention, compared to the other one that has a high retention or higher retention, and same thing for this compound. So the compounds with an intramolecular gene bond will be more retained, even if they are polar, even if they have an H donor, because in fact the polarity will kind of modify the conformation, you can, kind of imagine that it will fold the molecules and expose the lipophilic sites that will have more interactions with the PLRPS system. What if you don't have a control without intramolecular chain bond? What if you cannot? You have this idea of integrating the delta log P, where, so again, same thing, Julia studied the delta log P between octanol and toluene, and either way by calculation or by measurement, using the eLogD minus the PLRPS, where you could see that the main forces driving the delta log P is this H bond donor. And when you see here that when you have H bond donor and a propensity of having an intramolecular chain bond, you will have an equivalent lipophilicity between octanol and between toluene. And when you calculate the difference, your difference is close to 0 compared to when you don't have intramolecular chain bond. The lipophilicity will be completely different, and delta log P is a value that above 0 or below 0 that will show you that no matter what, there is no intramolecular chain bond. Of course, this is not always easy, and there are other complementary methods, such as the EPSA, that will give you the polarity, what I call the exposed polarity, or it's a polarity index, where through intramolecular chain bond, you will have less retention on a polar support, and that was developed by Gilles Goetz at Pfizer, and also the NMR temperature coefficient. So it was just to show you what we could do with chromatography in terms of lipophilicity. Again, that is a driver, or that has a high influence in drug design. So for me, the key concept I hope you will have today after this presentation is, so we can measure, and I would like to see more and more people measuring chromatography using, measuring lipophilicity using chromatography, because it's one of the most accurate method we can find. Of course, it has to be on reverse phase because it highlights the hydrophobic interactions. These hydrophobic interactions, or this retention, or this distribution of the compounds between solid phase and mobile phase is probably based on volume, surface, and conformation. And conformation is also driven by intramolecular chain bond. And there is a way to highlight intramolecular chain bond by chromatography by using log P, toluene, and water. Thank you, all of you, for listening to me. I really would like to thank the Analysia team, because working with them is a pleasure, and they have doing a great work working on the eLogD and on the alpha-LogD. That is the new generation of eLogD. And I would like to thank also all these great people through the different interactions I had with them, or also through the great papers and inspiring concept they have given all over the years. Thank you so much.
Thank you so much, Laurence, for your presentation. What we're going to do now is, I think we're going to hold off on any questions about your presentation. We're just going to go take a 10-minute break. And then we're just going to save your any direct questions for the roundtable sessions, if that's okay.
Absolutely. Perfect.
Okay. Great. Thanks, everybody. We'll see you in about 10 minutes.